Good morning, everybody. Good early morning to some of you. I know that people are spread all about the country. Welcome to treating siloxanes and H2S in landfill and digester gas. Today, your presenters are myself. I'm Kyle Snyder. I'm the Vice President of Business Development, Adventure Engineering and Construction. And we also have Bill Slotowski, the Chief Technical Officer of Venture Engineering. Just a little bit of background on Venture. I know there's misconceptions out there that we're just an equipment company, but the fact is that we are an engineering company first and foremost. Probably the premier process engineering firm in Western Pennsylvania. Began as process engineering. Now, as you can see, we've really spread out: electrical, project management, construction management, a very large civil structural group. So again, we began as an engineering company, and that's what we are. And we have the product that does that treats biogas as well. We're going to be extremely respectful of your time today. We will have a hard out at noon. We'll definitely give contact information. Additionally, we'll speed through slides to give you plenty of time to answer questions. Historically, it's been better to type your question, and then we'll just address it verbally. Just because when you get, we had 59 people sign up. I see we have 25 now. But when you get this many people on the line, it becomes a little more confusing. So if you have questions, you have options. You can type it, or you can give us a call afterwards, and Bill can spend as much time as necessary answering any questions that you might have. Additionally, this is absolutely not an advertisement for our, market-leading landfill gas conditioning system. We address our system, but if you have questions about other options out there, whether it's carbon or just taking, a single media and treating your siloxane issue or your H2S issue, those are questions that we can answer as well. We just happen to be experts in our system, and it gives a good basis for what we're going to talk about today. So, moving along, siloxanes are used in household and commercial products, as you can see by the pictures, certainly soaps and shampoos. They find their way then obviously into the wastewater and solid waste, and then they volatilize in the landfill and digester gas, and silica dioxide is formed during combustion, and that's what causes the issues. So in your engines, this stuff's essentially turning into a sand type product, and that's what causes the adverse impacts when you're trying to utilize it. And we'll definitely get more into what happens inside your prime mover with siloxanes during combustion.
The silica dioxide particles are, as many of you may know, are very abrasive. As Kyle mentioned, it's really you're taking the siloxane compound, which has it's a silica dioxide structure with organic portion of the molecule, and the organic portion burns in the combustion, and that goes away, but you're left with the silica dioxide backbone, if you will, of the molecule, and that SiO2 are very abrasive particles that cause a lot of fouling of the surfaces, as well as abrasive nature, so they're erosion on your parts, your moving parts in your engines and your gas turbines.
And we have some really good pictures of that to show you. We'll show the impacts right here on microturbines. The fouling, is obvious. Clean microturbine on the left, fouled microturbine on the right. In your boilers, I know that we've had more and more recently boiler projects. Reciprocating engines, which is, I'm sure, why most of you guys are on here, girls. You can see the effects on the turbo on the left there, and then on the pistons on the right. And by the way, if we go too fast, this presentation, just email us and we'll give you contact information at the end. email us and we'll send this presentation out to you guys. Depends what state you're in. You're being asked or told, I guess, to put post-combustion catalysts on your systems, and this is what can happen.
Right. Again, you're getting fouling in the media. You can see the honeycomb catalyst media photo on the left. All the white, well, grayish, but the white deposits are siloxane, silica dioxide residue, and it fouls the surface. So it doesn't, from what we understand in our conversations with various vendors, there's no chemical attack of the catalyst, but it does coat the surface, and then hence the catalyst cannot do its functional job because it's covered with silica dioxide particles. So the objective is really to clean the gas so the post-combustion gas does not have any silica dioxide in it. Obviously, the catalyst vendors would love to see 0 parts per billion in the gas. That's not really practical. But there are limits, at least we know of one manufacturer where it has about 100 parts per billion target for silicon dioxide compounds in the gas. And that's really what we're striving to achieve or improve that for siloxane removal.
So you can see the impacts that these siloxanes are having on your prime mover. You have a significant reduction in the efficiency of your engines or turbines. Makes your system unpredictable. Certainly you're going to add to maintenance costs. You're going to change oils many more times per year. Top ends, many customers are out there manually cleaning the heads and pistons. Right. Of course, you're increasing your likelihood of catastrophic failure as well.
So in addition to the deposits, the fouling, which creates corrosion, erosion of the rotary moving parts in your turbines and your reciprocating engines. The fouling from the deposits also have adverse effects on the heat transfer. So oftentimes engines and turbines will tend to run hotter when the deposits are inside the engines, which has damaging effects on the rotary equipment as well. So there's a lot of reasons to really minimize the siloxanes, get those out of the gas.
And before we move on, there is a question that pertains to exactly where we're at right now. So the question is from Patty: how can you identify the siloxane deposits from other corrosive matter on the equipment? How do you differentiate these materials?
Well, in landfill gas, certainly as everyone in biogas, off of digesters, maybe to a lesser extent, there are hundreds and hundreds of organic compounds, and so it can be difficult to just visually distinguish the difference. The white deposits are typically silica dioxide, which comes from siloxanes. To be absolutely sure, to answer Patty's question, to be really absolutely sure that there's silica dioxide deposits as opposed to other salts, for example, or other mineral deposits coming out of the gas or out of condensate. You really have to take a sample and have it analyzed in a lab. But from our experience in the majority of all the deposits, when you see the white powder depositing on the metal surfaces, I'd say 90% of the time you can be 90+% of the time you can be assured that those are mostly silica deposits coming from the siloxanes. Sulfur, switch gears here for a moment to sulfur removal, which is another problematic compound in your biogas. The sulfur is typically in the form of hydrogen sulfide, H2S, but there also are some mercaptan and disulfide compounds in your gas that oftentimes you want to remove those. The sulfur, in particular hydrogen sulfide, comes from gypsum, construction and demolition wastes that are found in the waste landfill gas, and then as it deposits or decomposes, you form hydrogen sulfide gas. Now, the effects of the hydrogen sulfide is to corrode metal piping and equipment, sulfur-bearing compounds, both the hydrogen sulfide as well as mercaptans and disulfides. They all have distinctive odors, release odors. I'm sure many of you are familiar with the rotten egg smell from hydrogen sulfide. Also, we're seeing a lot of regulatory limits being set on the amount of SO2 that can be released from facilities, and certainly when you combust gas that has hydrogen sulfide in it, the H2S gets converted to sulfur dioxide and sulfur trioxides when they're combusted. And due to these regulatory limits, there's oftentimes a need to remove the H2S to lower to meet these environmental regulatory limits for SO2. So, several of the treating options available. We'll just touch on 4 different broad categories. Venture has been involved with designing systems, supporting systems, troubleshooting process problems on all 4 of these categories. Upper left, you'll see it. Maybe some of you are very familiar with what we would call the solid adsorber, or scavenger, often called scavenger systems. They're commercially available solid medias where the gas flows through a fixed bed of this media, and then it chemically absorbs the H2S gas and holds it onto the media. The commercially available, some of them are as your Sulfatreat, Fairsorb, Sulfurite. There's a number of carbon-based medias that are out there by various vendors that all will capture the H2S out of the gas. These solid adsorbers are non-regenerable, and hence they're scavenger media, because the media is used, and once it gets saturated or loaded up with the H2S, then it's a throwaway. The positive note for using a solid adsorber is there's no SO2 emissions. We also have liquid absorbers, where instead of using a solid media, you can use a liquid that is scrubbed or sprayed in with the gas. It also will chemically bond with the hydrogen sulfide and mercaptans and gets held into the liquid stream. Typically, these are not cost effective for larger gas applications. There are some liquid absorbents readily commercially available. The downside, again, to a liquid absorber is you have this liquid stream you have to throw away. It's an industrial waste, and oftentimes it can get quite expensive when you're having to throw drum loads of a liquid absorbent into to dispose of it as an industrial waste. We have maybe we switch gears here for a brief second. There are a few additional questions from the audience. One question is normal siloxane quantities that you would not be worried about. So what levels of siloxanes would you not be concerned with? In engines, IC engines, the engine manufacturers typically have limits that the gas coming to their engine has to be below. These limits are set usually as 5 milligrams per meter cubed as a concentration of siloxane compounds. And some engines have 2.5 milligrams per meter cubed. When you get into gas turbines and micro turbines, you're talking down under 1 milligram per meter cubed. And as we said earlier, if you have a catalyst on your exhaust line, you'll need to get down well under 100 parts per billion. So to give you maybe a feel for what we've seen as typical values in the raw landfill gas, the untreated gas, 75 milligrams per meter cubed, upwards of close to 200 milligrams per meter cubed or some typical concentrations we've seen. So, you'll need to take the raw gas, 75 to 100 milligrams per meter cubed, treat it with a siloxane system to get it down below 1 to 2 milligrams per meter cubed in the treated gas prior to going into your engine, your IC engine or gas turbine.
The next question we'll take is the one that just popped up. We'll get to all of them, but it just really fits into what we were talking about. So how do you measure the amount of siloxanes in raw gas?
Yeah, so typically the analysis is using gas chromatograph with a GCMS, with a mass spectrometer on the GC. That is the best way to be able to speciate the different siloxane compounds. Now, there is not a standard EPA method that has been identified yet. I think there's a group of chemists in an agency that is considering developing an EPA standard method, but there's nothing absolutely developed at this point. When you go to lab and you ask if they have a GCMS, if they've, you really have to ask them if they've analyzed for siloxanes before, and also how many siloxane compounds they can analyze. Typically, there are 7 common compounds that are most prevalent, but there are up to 23 different siloxane compounds that can find their way into the landfill gas. And there are 1 or 2 labs in North America that can speciate all 23. And if you're interested in those labs, we'd be happy to, if you can contact us, we'll be happy to give you their contact information. Some labs only will analyze for 1 or 2 compounds, so you'll get a sort of a artificially low reading on your siloxanes. And there's definitely a wide variability in the repeatability of the analysis as well. That's why you really want to use a lab that has done this for quite a while and has a history of analyzing the gas for siloxane compounds.
Okay. And as we move along, the other questions are going to fit nicely into where we're going to move next. So we're going to hold off on those for just a minute.
Okay. So just completing some of the treatment options for this is again for hydrogen sulfide and sulfur removal. There are for systems that have higher concentration of sulfur, in the gas. The solid adsorbers, while they're cost-effective approach, they're not as effective when you have very high gas flows at very high concentrations, because the pounds of sulfur that you have to collect would require you to spend a lot of money with the solid adsorber medias. So for those larger systems, there are regenerative scrubbers. We just really touch upon a couple commercially available systems out there. Cameron has a Thiopac design system. It's a biological system that uses bacteria to digest the H2S out of the gas, and then as a byproduct of that process, you generate elemental sulfur. And Merichem has a similar scrubber-based system. It's called the LOCAT system. It's a liquid redox. Uses a chelated liquid to, again, take the H2S, take it out of the gas, and then converts it to an elemental sulfur byproduct. Certainly the one benefit, again, of the regenerative scrubber systems is, since you're capturing the sulfur as a byproduct, an elemental sulfur, there's no SO2 emissions when you take the treated gas and were to combust it in boilers or IC engines or gas turbines. And the fourth area of treatment option, which Venture has been working in tandem with TDA research on regenerative type adsorbing medias, where we've done some testing. We have some medias that will take H2S out of the gas, and then the media can be regenerative. The one aspect of using a regenerative media is, on regenerating the adsorption media, the regeneration waste gas will have to typically be sent to a pollution control device such as a flare, and so therefore the H2S is being released off of the media, and that forms SO2 in the flare exhaust during regeneration. So it's an interesting option for people considering either a regenerative scrubber system or even a larger solid adsorber scavenger system. But if you have emissions limits for SO2 that you're trying to mitigate, then a regenerative adsorbent may not be the best option for that type of application.
Okay, so David has a question about about H2S removal. He asks, which method of H2S removal would best fit in a case where the actual H2S levels have exceeded original treatment design? So he's basically asking which one has the greatest scalability.
Right. In the case of the solid adsorbents, the sulfatreat, sulfurite, those have pretty good scalability with when the concentrations are higher than you had in your original design point. The downside is going to be you'll still remove 99% very high levels of H2S out of the gas, but you're going to encounter the frequency of having to replace a media going to be much more frequent, because so for example, if you were originally designed that the media life would be 6 months, and then you'd have to add new media. Obviously, if you double say the concentration, that means now you're putting twice as much hydrogen sulfide, exposing it to the adsorber. Therefore, the frequency would be cut in half from, say, 6 months to 3 months. Scalability of the scrubber systems, There's a little bit of limitation there. You do have some scalability with a regenerative scrubber, but it almost has to be looked at on a case-by-case basis because those systems are quite extensive. Anybody familiar with a regenerative scrubber system knows that it's really a very complex. There's a gas contactor, but then you have a very sophisticated recovery system on the scrubber solution. It goes through a reactor to regenerate the liquid scrubber solution, and then a centrifuge to separate the elemental sulfur out of the reactor system.
Okay.
Another question while we're on H2S is what is the best method for removing thiophenes and mercaptans when H2S is not a problem? So with mercaptans and thiophenes, there are, again, the solid adsorbents are probably the best approach because there are commercially available. Sulfur Treat has a whole family of products as well as various carbon-based medias. There are impregnated carbons. There are some different multi-layered carbon systems that have ability to remove hydrogen sulfide and mercaptans, or have a high percentage capture for thiophenes and mercaptans. Your regenerative scrubbers like the Cameron Thiopacks, the Locats, they're predominantly targeted to remove H2S and don't have a lot of mercaptan capture capability. So definitely, if you're only trying to target mercaptans, thiophenes, the solid adsorbents, and selecting a solid adsorbent that would be, more preferential for those type of sulfurs would be the way to go.
Very good.
Continuing back towards, we'll touch upon the siloxane adsorption system, a gas conditioning system to remove siloxane, predominantly targeted for siloxanes, but it does target other non-methane organic compounds, VOC organics, hydrogen sulfide to a little lesser degree, and water, moisture. Our venture system is a selective regeneratable adsorber system. Typically, depending on the gas flows and the concentrations, it will be either a 2 or 3 media mix system. Oftentimes we're using activated alumina, silica gels, molecular sieve type medias. We'll use a blend of these medias, again based off of the concentrations and the types of compounds we're looking to remove. Because it's a regenerative system, there's no carbon used because carbon poses challenges to regenerate activated carbon.
And this is a good time to answer the question that was posed by Justin. And he asks, is saturated carbon considered hazardous waste, and can it be disposed of in a landfill? And to begin the answer to that question, as you just learned, the venture system does not use activated carbon. And I can answer this next question, but Bill can do it a lot more technically. So can you answer the question, Bill, about the landfill disposal?
Right. So Justin's second part of his question is, can the saturated carbon be disposed of in a landfill? And the answer to all these medias, that even goes back to the scavenger H2S medias, is it's really depends on whether you have any other hazardous compounds that adsorb onto the media. So what you need to do is there's an EPA, a T-clip, often referred to as T-clip, analysis that's run on the solid media. They look for if any hazardous compounds, heavy metals, cadmium, arsenic in particular, will leach off the media, and if the concentration of the leach compounds exceeds the established EPA limits, then it has to be disposed of as a hazardous waste. Oftentimes the compounds are not high enough concentration, and it passes this EPA T-clip test method, and it can be disposed of in landfill. So to answer the question, I guess it's really a qualified yes, but you do have to have the media tested for other compounds. The one particular compound that we've seen fail is some landfills will have when they run the test method, they'll find arsenic, and the arsenic levels are higher in the media than what the EPA method allows, and therefore they have to be disposed of as a hazardous waste, as opposed to a waste that can be landfilled.
Just speaking for the venture system, we have 20+ systems out in the field right now, which involves a good number of media changeouts. And I don't believe that we've had any failed T-clip, have we, Bill? I know the one was relatively high in arsenic.
Yeah, the one in New Jersey. We had one site in New Jersey when they changed the media out. It was very high, borderline high for arsenic, but did not fail. So we did not have any that we're aware of the systems that have had media change fail for the T-clip test. I have seen several H2S scavenger type medias where they've failed for arsenic. But interesting, on several landfills where they might fail one time, they'll test it the very next time they need to change the media, and the second time it will pass the test. So it really is, if you fail with for arsenic or one of the other heavy metals, it doesn't mean that you're going to every time continually fail that test method. Back up a second.
There we go.
So just to give you a very an overview of the process, the siloxane adsorption process that Venture has. We're showing in this schematic here two separate adsorber beds. We'll call them adsorber A and adsorber B. You see the process gas will flow. There's a series of valves, automated valves on the system. We're not showing the valves here in this simplified schematic, but
there is some pictures coming up in the next couple slides.
Right. But the process gas would be treated through one vessel. So for example, we'll say adsorber A is in production. It's flowing process gas through adsorber A, and then it's going through some post filters for particulate, and then the gas would then flow to your gas turbine or your boiler or your IC engine, your treated gas. While the process gas is flowing through adsorber A, adsorber B would be in a regeneration mode. And we're showing that from the bottom up, where the regeneration gas would first go through a blower that pushes the gas into a heater, because we use heated air to regenerate. That hot air would flow up through adsorber B. That heated air, as it flows up through the vessel, causes the siloxane compounds, the organic compounds, water, hydrogen sulfide, all the contaminants that adsorb on the media, the heated air causes that heat, causes them to release or desorb off the media, and then that's swept over to a flare for pollution control, so that the regeneration gas is then thermally destructed in a flare or thermal oxidizer unit. Then after adsorber B, the regeneration is complete, then the valves, as I mentioned earlier, that they'll automatically switch, and then processing gas would switch from adsorber A over to adsorber B. So B would then be in production, and then adsorber A is taken offline, and it's ready to go through its regeneration process. So the process, again, in a summary, the gas is processed through one adsorber, the other adsorber is offline being regenerated, and then periodically, and this is all done with a PLC controlled, is the beds would switch from A to B and then back to A, so it toggles back and forth. As I alluded to, so that switching for the regeneration, there's two ways of that switching taking place. Typically, in our original design was time-based regeneration, and what we mean by that is, so the production cycle on one adsorber would be typically it's 24 hours, one day, and then we switch once a day from A to B, and then 24 hours later we go from B back to A, and that cycle repeats over and over and over. Now we're also looking at the process control-based regeneration, where we're working with some vendors for online analysis of siloxanes using FTIR, Fourier transfer infrared spectrometers, to analyze the gas, the treated gas, and switch the beds when we see the concentration in the treated gas starting to decline. Then we would make the switch, as opposed to just strictly on a time base. Again, some of the benefits and procedures, processes of our system. We would see extremely low dew points, oftentimes minus 40 or better, because the media dehydrates, adsorbs water as well as siloxanes. 90% removal of non-methane organic compounds, halide, halogenated, it's chlorine, fluorine-based organics, 70%, up to 70-75% removal of those compounds out of the gas, up to 95% removal of H2S. That's cycle time dependent, and the reason we say that is that the H2S will have the capacity, the medias have different capacity, holding capacities for these different compounds. So on a 24-hour cycle, you'll still have siloxane removal where your effluent is less than 100 parts per billion, but your hydrogen sulfide breakthrough will occur before the 24-hour period.
So we're going to hop back and answer Graham's question about the scalability of these systems for smaller applications. I can say that they're scalable to any size, to the extent where for the regenerable system that we're currently discussing, we have applications as small as 400 SCFM. There's a good chance that your question involved the system smaller than that. Recently, we have multiple inquiries for application of 30 to 150 SCFM. Economically, that doesn't make sense currently for the regenerable system. But yeah, there's options. You know, we have standard fixed bed systems where we would analyze your gas and then provide custom media specifications for that project.
Right.
So there is scalability, again, for the regenerable system, where prices, start in the $400,000 range, frankly. It doesn't make sense to a lot of applications. Although we are currently designing systems significantly smaller, it's just not ready to go yet. So we do have passive, we would have a passive solution for something smaller than that.
Right. And the primary reason when you get to very, very low flows, say 100 SCFM of gas flow, a regenerative system, you do need a pollution control device like a flare or a thermal oxidizer, because the regeneration gas has to be thermally destroyed. You can't just vent that to the atmosphere because it contains all your contaminants in that waste and that regeneration gas. So if you only have, and to run even a small flare to maintain the temperature in a flare up over 1400 degrees centigrade, or I'm sorry, 1400 degrees Fahrenheit, you would need a fuel source. So you would need to be utilizing some of your biogas in the flare. So if you only have 100 CFM to start with, and your flare, even a small flare, requires 50 to 75 CFM to run the flare, you effectively have to take all your biogas away from the treatment to just run the flare. So it doesn't really practically make sense to treat that in a regenerative system. But as Kyle mentioned, a passive system where you'd have the same medias, same types of medias, multimedia mix, can get your very high siloxane removal, but since you're not going to regenerate them on site, you would have to plan on media replacements more often. Perhaps every 3 months, every 6 months, upwards of maybe 9 months to a year, depending on the size of the vessels.
And then to answer the obvious question based on that, because of the more media changes, the media that goes in these is, all three medias are less than $2 a pound. Some of them significantly less, some of them around $2 a pound.
Yes.
The typical lifetime for the regenerable media is we like 12 to 18 months. 12 to 18 months for sure, unless the things that have negatively impacted that time frame have been free water, or the gas has changed significantly. We did have a project in Las Vegas where just significantly higher NMOCs were seen after installation of the system. When I say significantly higher, I mean 10x,
right?
6x to 10x, big.
10 or more.
Yeah, like a huge.
So
or your H2S changes, or something happens to the gas. But yeah, so 12 months is good for your O&M.
For planning purposes.
Yeah, for planning purposes, say 12 months. We have a system in Massachusetts that has very high H2S, but that media has consistently lasted longer than 18 months. So for planning purposes, say 12, and we think it's going to last a little longer than that for sure. The next question is, do newly regen beds strip CO2 from the processed gas when first cut in?
And the answer to that is there is some adsorption of CO2 on this media. You'll see that at well, let me back up. When you first put very fresh, brand new media in the adsorber, the first 2 to 3 cycles, this adsorption of CO2 is very high, and we actually have a pre-repressurization step that we run, so we don't shift that high methane content going over to your engine or your turbine right after the first cycles on a brand new media. Subsequent to that, the CO2, there will be a slight increase in CO2, but we do, when in our process of repressurizing the media, from switching from a regeneration back to production, we'll repress the bed with your biogas, and in the process of doing that, that gas is then vented over to the flare, so that CO2 gets adsorbed on, so the bed is preconditioned prior to switching. So when you switch back to production, there's a very minimal to really no detectable CO2 bump in switching. So here's a photograph of a 3-vessel adsorber. We're showing on the right-hand side there. You can see the one adsorber has a big A on it. That's the vessels. This is a system where, again, one vessel or 2 vessels would be in production with the other vessel in regeneration. Also on this skid, what you'll see is, maybe it's a little difficult to see, but in the foreground is the control panel that has your PLC that's doing all the control of the sequencing the valves, as well as the blower and the heater that we talked about for regeneration that heats the air. That's all on the skid, and that is all controlled. The set points and the switching of turning them on and off is done via the PLC on the skid. So truly it's a system that is put on the skid. You set on a foundation at your site. You bring your process gas up to the inlet flange and the discharge flange, hook up your power feeds to the system, and you're ready to rock and roll with treating gas. A couple other bullets on this slide, some things we've already touched base on, and some questions from the audience. Typically we see a 24-hour time cycle for production. The media life expectancy, as we mentioned, is 1 to 2 years. We have systems in installation both in low pressure, and we would define low pressure as, say, less than 10 psig, and high pressure applications where we're upwards, and we actually have one system where we're close to 200 psi for gas turbine applications. So we'll treat the gas on either the low pressure or the high pressure side of the plant.
This is probably a decent time. I know that we've put Gene's question off for a while. Can you comment on the variety of post-combustion catalysts used and any observed differences in SiO2 buildup on them?
Okay, so oftentimes there's a need for CO catalysts, and there's also a catalyst used for NOx. And some systems require both CO and NOx catalysts. Some emissions require only one or the other. I guess we have, maybe knock on wood, we've been somewhat fortunate and not, systems that have had our siloxane treatment in service. The catalysts haven't really been compromised, so we haven't really seen where one is more problematic over the other. I do know where some folks, as a safeguard, is a sort of a secondary line of defense when you have both CO and SCR catalysts in the system. They will put a third honeycomb matrix, which is the essentially the catalyst structure without the active platinum, palladium, activated metal, the catalyst itself, which is the real expensive portion. They'll just put the honeycomb substructure up front of that, so allow the gas to flow through that. So essentially, the silica dioxide is depositing on the surface. It would deposit on that pre-treat chamber, pre-sacrificial, prior to the actual catalysts themselves.
Okay, the next question is how many systems we have operating in gas turbine applications? Off the top of my head, I'm going to say 3. So, correct?
We have.
It would be Apex, Celinda.
Right. Well, yeah. There's actually a fourth. Well, we have another system there, more recent system that is where the gas turbines are actually 16 miles away. We have 3 systems where the pre-treat, siloxane pre-treat, I would say, is directly coupled at the same site to the gas turbines, and then 1/4 system that goes into a dedicated 16-mile pipeline. And of course, all 4 of those systems do have both SCR and CO catalysts on the emissions stream coming off the turbines.
Very good.
Okay. Where we're trying to advance our having some technical difficulties getting our slide here, pen.
We outthought ourselves on the technology here.
Okay. One of the things while Kyle's looking into why our slide doesn't seem to want to advance to the next screen, but the photo you see there on the right, as I said earlier, is a 3-vessel adsorber. Oftentimes we have a typical system. It would be two adsorber vessels, an A and a B train switching back and forth. As I said earlier, A's it would be in production, B's a regeneration system. We also have systems that our largest systems we've done still have 2 trains, 2 treatment trains, but to keep them on skids and keep them shipping height, so that as opposed to large adsorbers that would have to be shipped separate, mounted onto foundations, we use the photograph you see right now on your screen is one of our larger systems. This treats gas up to we have 2 installations of this size. Actually, that's a third going to be commissioned in a few months. But the 2 that are installations now treating 12,000, 13,000 SCFM of gas. What you see on this drawing here is the 6 vessels where the red valves are right in the middle of your screen. Those are 2 trains of 3 adsorbers each, treating the siloxanes. And then since these have SCR catalysts, and we want to ensure that the SCR and CO catalysts and maintain the low, less than 100 parts per billion siloxane concentrations in the effluent gas, the 2 vessels in the foreground would be a polisher. So we use a second stage of polisher, non-regenerative polisher vessel. in the upper right corner of the diagram there, you see those two blue vessels. Those are the regeneration blowers that blow the air for regeneration. And of course, all the red valves in the middle, those are just the red actuators. But those are the series of valves you see that do all the switching between switching the beds from regeneration to production. Again, all that control is done automatically with PLC that's mounted on the skid. Now, this system, again, because of the size of it, instead of one skid, it actually shipped as 4 separate skids. But again, all the electrical instrumentation, valving was all pre-wired, pre-installed, so it made for a fairly quick and easy installation once it was brought on site.
Here's actually it's a partial list, pretty complete, but nevertheless partial, of Venture's gas conditioning systems out there in the world. Just in the last month and a half, we've shipped 4 systems. And I really wanted to get to this. I know it's 11:58, and I promised you guys would be out by 12. We will stick around a little bit longer, but yeah, I mean, I just want to make sure that we get 99% of this done before noon. So if you have other plans, you can hop off. But this is a snapshot of a project. One Yambacher 420. They were having significant fouling, as you can see. They were doing top ends every 4,000 hours. They were changing plugs, or at least cleaning them off,
Right.
which took a significant amount of time, twice a month. They were doing oil changes twice a month. So again, this is a single engine site, but you can think about this as a 4
and
or
as
5
Kyle,
engine site.
and as it says on the slide, the catastrophic engine failure, siloxanes cause, and an earlier question from the audience was, how do you detect siloxanes? Well, in this case, because of the severe fouling they were having, they did indeed send their deposits to a lab and had them analyzed, and confirmed indeed they were silica dioxide coming from siloxane. So they knew that these deposits were indeed, derived, or the culprit was siloxane compounds themselves. So that was what triggered this client to want to put in a system in their site. And it was a smaller system. It was one of our first systems we put in. It's since been running. We have 15,000 hours in operation there, but this slide hasn't been updated. It's really 4 years, so they're in excess of 32,000 hours of operating time with this system.
The slide was updated, it just wasn't saved as updated.
Yeah. The inlet, kind of the gas composition there, it was, 50, you want to switch back to the slide? The middle there, you see the raw gas, some questions we had earlier too on the concentrations. This gas was 55 milligrams per meter cubed as siloxane compounds, and the target was to get less than 5 milligrams per meter cubed siloxanes. That was again what the engine manufacturer requested, and they also are getting greater than right around 75% NMOC removal, and since then they've seen these targets exceeded on a fairly continual basis. Next slide. Some of the actual performance. We've seen that indeed they've actually been less than 100 parts per billion, which translates into less than 0.1 milligram per meter cubed silica. They're still running. Again, they're still running below 120 parts per billion. The VOCs and the sulfur have been, they've experienced very high removal efficiencies. They're back to normal plug schedules. Their oil testing has shown that the oil is very clean. They haven't had any overhauls. They bore scope the engine. It's clean. They don't have any plans, in the foreseeable future to be doing any engine overhauls, at least attributed to Siloxanes. For this customer, they were hoping to get a payback of about a year to a year and a half, and based off of this, because they did some performance on some hopeful improvements, and because the engine the performance was so dramatically improved, the payback was much less than 1 year payback on the capital investment.
So really, just let me answer the question from Patty before we this is actually the end. So how much did the application cost that you have on the screen? So I think she's probably referring to the 6-vessel system. Now that 6-vessel system included the carbon polisher as well. You'll generally need a carbon polisher. We'll generally recommend a carbon polisher only in situations where you're going to have a turbine, or you're going to have the catalyst SCR on the back end. So this was a high-pressure turbine project that happened to have catalysts on the back. So with the carbon polisher and a 6-vessel system, that's right around a $2 million system. So our systems range from $400,000 to $2 million, and that would be for 400 SCFM and above. Now again, if it's just a passive vessels and media for something less than right now 150, we kind of have a gap in the 150 to 400 range there, I would say.
Right. So less than 400 SCFM, you probably passive system typically makes the most economic sense.
Right. And again, that's just 2 vessels with media in, and that would be about 18,000 pounds of media at less than $2 a piece. So 2 vessels plus the media.
Typically, the reason you would want to use 2 vessels is we would recommend a lead lag configuration, manually valved, so you have the option of either running in a lead lag configuration, or actually you could even run 1 vessel in production, have a 2nd vessel standing in the ready. So when you have to change media, you can isolate the 1 vessel, still continue flowing production gas through the 2nd adsorber vessel. As opposed to, obviously if you had 1 vessel, when you have to change the media, you cannot treat the gas when you have to change the media out with just 1 vessel configuration. So those systems are smaller, and we've designed systems both in carbon steel and in stainless steel. Our standard regenerative systems are usually 304 stainless steel piping, process piping, and the absorber vessels themselves are 304 stainless steel. We've done carbon steel. We've also done 316 stainless steel.
Okay, so just in summary, and just let me point out that in the chat area, I did put Bill and myself. I put our email addresses. Our phone number is listed right here on the summary page. On ventureengr.com, you can find both of us with our email addresses. Well, I know my email's on there for sure, but I'm also going to send out a follow-up email just to thank everybody for hopping on, and I'll have both our contact informations on there. So again, I want to thank everybody for hopping on, and please give us a call or send us an email with any questions that you might have. And when I send the email thanking you, you can certainly get back to me and ask for a copy of the presentation. There really is a lot more, but we do what we can do in an hour. And so again, thanks for hopping on. Have a good day.
Thank you.